Okay, morning everybody. So, just a few things before I begin, because I guess few of you were not here when we were talking about the questions asked during the lecture. So, actually, Sadia is not here. She asked me a question, and that was about that I took the constant coefficients for the Riccati equation, and the equation says that it can have variable coefficients. So I'm just writing down the problem where you have do you see? Now this is not a constant coefficient. This is a Riccati equation. And anybody can guess what is the one solution, because unless you know the one solution, you can't find the solution to this problem, because the this is the transformation that I need to use to solve it. Kyunchi, what do you think? What is one solution by inspection? Just put y is equal to sine x here. Then tell me what happens. It will be the solution, because d by dx sine x will be cos x, and over here we will get cos x. So one solution is y is equal to sine of x. The other thing that we discussed was the singular solution. So suffice it to say that when you have a solution with an integration constant c, which can be determined from the initial conditions or the boundary conditions, that is your general solution. And the one that does not have c in it, or one that cannot be obtained from c, that is called the singular solution. So this is no matter whether you're dealing with a higher degree differential equation or a first degree nonlinear equation, you will have these solutions which will not involve c, or which cannot be obtained from c. Okay. So just before we begin and talk about the second order differential equations, just to recapitulate what we have done so far. So we started off with the nomenclature about differential equations and this comment that generally things vary with space or in time, and that is why you have the derivative with respect to x or time. And then we went on to solve the linear differential equations. We learned methods how to solve a first order, and we talked about the applications like the radioactive decay, Newton's law of cooling, and stuff like that. And then we went on to do the nonlinear ODEs, first order nonlinear ODEs, and we talked about Clairaut's equation, Riccati's equation, Bernoulli's equation, and the most important lesson was that you have transformations that reduce a nonlinear equation into either a separable ODE or a linear ODE that you know how to solve. And most importantly, these equations have practical applications. I showed you that if you have a mass and it is accelerated by a particular time-dependent force, then you can get a Bernoulli's equation. And in the reflection of particle by a mirror, you can have this higher degree differential equation. So all these equations because over here we are talking about mathematics for physicists, so we need to know where these things can come from. So now the next topic is the second order differential equation. We are going to talk about first degree, second order differential equations, homogeneous and inhomogeneous. People call them non-homogeneous as well. Both terms are in vogue. So most of the physical world around us, the macroscopic world around us, is governed by Newton's second law, right? And I told you that he had to invent calculus as well, so this equation in principle can be written as, you can write this as well, but of course you can express it as d2x over dt square as well, and this is what the force is equal to. So you see, in terms of velocity, this is a first order differential equation, but in terms of space, it's a second order differential equation, and this is what we are going to deal with. But we should know the power of this equation. So if you have to find out how the planets move, you know, under the influence of the gravitational force, you just need to write down the force and you solve it, and you come up with this remarkable result that these are not circles that was initially anticipated, because people thought that they ought to be symmetric because, you know, an infallible creature creates it. It ought to be perfect circles, but it turned out to be an ellipse. So all these things you can calculate. A particle subjected to a magnetic field, you solve this equation, you get it. In Navier-Stokes equations, I do plasma physics, so all the time we write down the Navier-Stokes equations, and of course this equation is an essential thing. You need to know what are the forces acting on the system. So as I told you earlier, unlike the first order differential equation, once you take the antiderivative, in fact antiderivatives of this equation, you will have two constants, and the whole idea is to find out those constants. So what is it that is different here fundamentally than a first order differential equation is the geometry also, because here you can have 2 points, and that 2 points are minimum to define a boundary. So essentially you will now have a new class of problems, the boundary value problems, which you cannot have in the first order differential equation. Okay, so this is like the fundamental stuff that you need to understand, and before you embark on the journey of understanding what all this is about. And just like the first order differential equations, over here we also have to think about the existence and uniqueness. Of course, existence and uniqueness holds here as well. So the solution not only would exist, but also it will be unique, and uniqueness is essential because if you're dealing with the problem of the physical world. So I'm going to start with the boundary value, and just to write it down in a way that you generally. So let's say if I have a point A and a point B, and I define a boundary here, so it means this is my interval now, over which the differential equation would exist, and I will talk about the existence of the solution and the uniqueness of the solution. But what are the different conditions can you think of that I can pose here? So first things first, if I say I asked you earlier also that if I have a force-free system, and if you're a theoretician, then is it difficult for any of you to convince yourself that the particle will execute rectilinear motion and nothing else? Is it clear to everybody? Rectilinear motion, straight line motion, the rectilinear means straight line motion, Sirat-e Mustaqim, yeah. So can you show it? If I write, let's say, m d2x over dt squared, and I write like this, so any of you who doesn't know how to do it? So the thing is that you have to integrate it twice. First you integrate it, you will have dx over dt, which is the velocity, equal to c, and in the next case you will have x of t is equal to c of t plus c1, and that is how you know that in the absence of force the particle will move in a straight line. So in order to completely determine the system, what is it that I need to evaluate?
Initial conditions.
Sorry, say again.
Initial conditions.
No. Not the need. What are the things that you need to determine looking at this equation? But they are associated with which particular physical quantities?
Position.
Velocity.
आप बताएं. Yeah. What is it that you will determine once you determine C here?
Velocity.
Velocity. And what will you determine if you determine both the constants? Position. So you have to specify initial position and initial velocity to draw the trajectory that particle traverses. Okay? So this is the problem. Geometrically speaking, what you say is that in a first order differential equation, all that you need to do is to specify a point. But over here, when you, so let me draw it slightly in a curved manner. So now I need to also draw a tangent. Okay? So you need a point and you need a slope at. But when you have a boundary value problem, you have two different points, then what are the different ways that you can actually specify things? Because now you are defining something over an interval AB. And on 2 points, please. No, that is okay, but all I'm saying is, if I've just told you what is it that you need to completely determine the system. So now what are the different ways that I can actually find two constants? If I have these 2 points, what are the different ways that I can actually find the two constants? Excellent, yeah. So either I can say y of A is this, y of B is this, I can determine thing, or I can say y of A is this, y dash of B is this, or y dash of A and y dash of B, and so I need two conditions to find out the two constants. Okay? So now I will just write down the general condition that you need for the boundary condition problems, which will take into account all these possibilities. So alpha 1 y of A plus beta 1 y dash of A is equal to gamma 1, and alpha 2 y of B plus beta 2 y dash of B is equal to gamma 2. So as you can see, all these possibilities that we have just discussed, they are present in these general boundary conditions. So just like the first order differential equation, over here you will also realize something, that although we talk about the existence and uniqueness, but over here, over this interval A and B, if you give certain boundary conditions, you again will find something interesting. So let me do that problem for you. Up till now, if there is any question, please ask. And please ask the question using the mic, because I was seeing comments, so some people were complaining that we can't hear the questions. So that is why Parvez Saab keeps asking us to ask questions using the mic. Okay, so we now just, so very simple problems can be extremely instructive. So let's say I have a differential equation and I'm not at the moment trying to devise any way to find the solution of this differential equation, but just assume that the solution to this differential equation is C1 cos 4t plus C2 sine 4t. And let's say my boundary condition is x of 0 is equal to 0 and x of pi by 2 is equal to 0. So it means at t is equal to 0, x is equal to 0, and at t is equal to pi by 2, x is equal to 0. Now find the values of C1 and C2, because that is all that is in your way to completely determine this.
C1 equals 0.
Yeah, so when you have 0, so this will be 0, this will be 1, and C1 will be equal to 0. So what you are left with is x is equal to C2. Now do it. This is 0, C2, and sine is what? So sine of 2 pi is 0, sine of n pi is 0, right? Now tell me what you can say about the solutions here. Infinitely many solutions. Why? Because no matter what you choose as C2, eventually it will satisfy because it is going to get multiplied with a 0. So you will have infinitely many solutions, right? So now just change the boundary condition, and this is the whole instruction. You do this, x0 is 0, that remains the same, but you just use this, x pi by 8 is equal to 0. So you already know that C1 is equal to 0, so you don't have to do that, but now you try and find out this using this boundary condition.
C2 is 0.
So you will have sine pi by 2 is what? 1. So you will have C2 is equal to 0, and your solution will be x is equal to 0. So some of the friends in the comments wrote that my use of board is not very good, so I admit it is pathetic. I'm not very systematic. Some people write things in a very orderly manner. So my use is also as cluttered as my mind. So anyway, so this is a unique solution, okay? Because I have x is equal to 0, which is a unique solution here. Now what will happen if I use this boundary condition, which is, so that the friends online don't complain, I'll try and be more aware of this disorderliness and try and write. So the next third boundary condition is x pi by 2 is equal to 1. X of 0 is 0 still. So I know that C1 is 0, and now I use this condition. Now tell me. आप बताएं मुझे जरा प्लीज. Do it. You have to plug this in here, and you need to tell me. Yep. So this will give you. This will be sine 2 pi, and this is C2 sine 2 pi equals 1. So this is basically 0. So can you come up with any value of C2 that will make the left hand side agree with the right hand side? So this way you have found out, when you say no solution, why do you say that? There's an alternative way of saying this. When I say there is no solution, what is the other statement that I am making, which is more useful from the.
We get contradiction from the conditions.
That the boundary condition is wrong. Okay? So you just can't impose boundary conditions out of thin air and expect that they are going to make sense. Okay? So this is something that you need to keep track of, that when you apply the boundary conditions, you do not get a non-physical answer. Okay? So it means the choice of the boundary conditions is incorrect. So again, just like in the first order differential equation, you in the boundary value problem, you still have a unique solution, infinitely many solutions, and no solution, which means that the chosen boundary conditions are wrong. Okay? That is a more appropriate way rather than saying no solution. To understand, comprehend things in a better way, you need to appreciate this, that the boundary conditions which are chosen here are wrong. Okay? All right. Questions, please ask. यहाँ पे आवाज echo करती है. Okay. Must be some reason. You can prove this thing. Hassan Saab already has probably done that. That differential operators are linear operators. So linearity property holds here, right? So if you multiply it with a constant, you can take the constant out, and if you apply, let's say, differential on a plus b, so it will be differential of a plus differential of b. So that is why differential is a linear operator. So when the antiderivative is also a linear operator. So these operators are linear operators, and you should know this, that these are linear operator. And I'm going to talk about the second order linear differential equation. So there is a theorem which says that the solution can be written as a superposition. Okay? So you have nth order differential equation, you will have n solutions. So what do you understand by this superposition principle? Let's say I say that there is a second order differential equation which has a solution x squared, and I also say that there is another solution which is x squared log of x. So let's say I say that these are the two solutions of a particular differential equation. So if you apply the superposition principle, what is the other statement that you can make? Gigi, please. इसको on कर लीजिएगा, please.
Sir, I think we can say that the different solutions are for different domains, and by
No, but
superimposing.
domain is the interval is defined. So whether it's a sorry.
May I tell what we can say in other words?
Pardon me?
May I tell you what we can say in other words? I mean, this statement of superposition principle.
You don't have to ask like in just a moment.
Yeah.
Just to clarify, if I am defining a boundary or I am defining an interval of a differential equation, both the solutions are defined on that interval.
Okay.
That is already known. But the thing is, if I am writing down a second order linear differential equation and without proof I have told you that the solutions can be written as C1 Y1 plus C2 Y2 plus so on Cn Yn. So let's say if I have a differential equation with these two solutions,
Yes.
so using this superposition theorem, what is it that I can say?
Yeah, sir, I think by interval or by domain, I mean we can also say that in terms of time also, and in terms of के क्या वो internal conditions उस पे apply हो रही है या externally कोई force है, या मतलब different effects की वजह से हमारे पास जो different solutions आ रहे हैं.
अभी हम सिर्फ we are talking about homogeneous linear second order differential equation. So it means I am not considering any input.
Right.
It's just the natural response of a system. अभी हम उसके बारे में बात करते हैं. I'll tell you, but the thing is, just using this principle, what is it that you can also say? If I say, just a moment, let him answer. In the process, I guess you will also become clear.
So we can say that linear combination of solutions is also a solution of differential
That's a
equation.
linear combination. So what it means is that if these are the two solutions, then c1x squared plus c2x squared log of x is also a solution of this differential equation.
Sir, because the operator is linear.
Only because of this.
Yeah.
Superposition does not hold for nonlinear equations.
Yes.
Well, there is a superposition principle, but I'm not going to get into that. That's a different kind of thing. But the superposition that we understand is and the theorem holds for the linear operators, for the linear differential equations, right?
I was asking about the reason behind it. Like why basically we can write
This is the property that the linear systems exhibit. And seeing is believing. I can write down an equation and I'll say that this is the solution. You will plug it and you will find out that this is the solution. You will plug this one independently. You will find this is a solution. And then you will plug this whole thing and you will also find that this is also a solution to that differential equation. That is the property that it exhibits. Okay? Of course, we can always prove things mathematically as a theorem, but in 8 lectures, we can't afford to delve deep every time. The other thing that is closely associated with this is what Hassan Saab has already talked about, but I'm going to talk about that as well. So this is function space, right? This is not, again, at the cost of repetition, I'll say that when we talk about vector space, that is a geometric space. When we talk about function space, there is a very close analogy, but when you say that cosine and sine are orthogonal functions, that does not mean that cosine and sine are, placed perpendicular to each other. That is meaningless. So there is no geometric meaning that is associated with function space, but it has the same properties that of the vector space. And when we'll go and talk about the orthogonal functions, you will see that we start with the same nomenclature that we use for the vector space, but now you have a function space. But cosine and sine cannot be construed as, when they are orthogonal, that this is, cosine and this is sine and they are at right angles to each other. This is not so don't try and associate the same geometric meaning because this is function space. The other thing is that you will write that C1 F1 plus C2 F2 plus so on up till Cn Fn is equal to 0, and this holds if and only if C1, C2 up till Cn are all 0.
Yes.
There is no other way that this relationship can hold or this requirement is met. And what does that mean? It means that one cannot be expressed in terms of the other. So let me give you an example. So let's say you have y is equal to x and you have y is equal to modulus x. So y is equal to x will have this geometry here. You can in fact go on and on. But y is equal to modulus x will be this. So there is no way that you can obtain one from the other. If you can express one in terms of the other, that means that is linearly dependent. And if there is no way that you can express one in terms of the other, then they are linearly independent. So let's say if we are dealing with functions, how can we imbibe this idea further? So the best way is to do an example. So let's do an example. f1x is equal to cosine square x, f of 2x is equal to sine square x, f of 3x is equal to secant square x, and f of 4 is tangent square x. And you have to prove that these are linearly dependent on an interval minus pi by 2 to pi by 2. So what it essentially means is that C1 F1 plus C2 F2 plus C3 F3 plus C4 F4 is equal to 0 can be shown to be 0 without assuming that C1, C2, C3 and C4 are all zeros. So it means these functions somehow can be expressed in terms of the other. So now you have to prove it by choosing the appropriate C's other than 0. If you can choose C's other than 0 which will make this expression go to 0, then it means that they are linearly dependent. So just do it. Look at the combination. So let's do it for this choice. I want you to make sure that this choice works for you. Now do it and tell me whether it works or not. 1 minus 1 nahi, this is not 1 minus 1. What it means is, yep, okay, so F1 and so C2 and C1 are 1, so cosine square x plus sine square x is 1. Then 1 minus secant square x, that is?
10 square x. And 10 and 10, 10.
No. This is 1. So 1 plus tangent x, tangent square x is secant square x, and secant square x minus secant square x is 0. Those of you who are not used to this kind of thing, just do it on the paper and tell me that, do it and tell me whether you have done it or not. So this shows you that there is a choice of C's other than 0 for which you can show that this is equal to 0, right? So that shows that this is linearly dependent. Similarly, you can also show that something is linearly independent by showing that there is no choice of C's that can ever make it 0 except all C's going to 0. So these are very important fundamental concepts that you need to understand. So function space, I have already told you geometrically it doesn't make sense to talk functions like vectors. But when we talk about the linear independence of vectors, when we say that one vector is linearly dependent on the other, can you give me an example? I mean, let's say this is a vector and I want to show geometrically that there is a vector which is dependent on this particular vector.
Velocity or momentum एक दूसरे के dependent एक दूसरे के direction में नहीं होते.
No, I mean, I'm just talking about vector space. This is a vector and you want to construct another vector to show that it is linearly dependent.
So it's a constant multiply करने के.
Yep. Yeah, so I can either make another one with a bigger magnitude or I can cut it down, the length can be shortened, but both can be expressed in terms of the other. So let's say x2 is equal to 2x1 or x2 is equal to 0.5x1. All these things point to the fact that these are linearly, and geometrically speaking, they are, one is exactly onto the other, right? There is no direction difference. Another criteria which is also a very useful criterion to check the linear dependence and independence of the solution is the Wronskian. and which says, so let's say, so what you have just seen, that you have a second order differential equation, and in terms of the constants, what are the things that you need to determine? X and X dash. Similarly, if you have a third order differential equation, what are the things that you will have three constants, and what are the things that you need to calculate? X, X dash, and X double dash. So Wronskian tells you that if you have, let's say, second order differential, because we are going to deal with the second order differential equation, in principle, you can have nth order differential equation and you will write down n minus 1 derivatives. But for a second order differential equation, all that you need to do is f1, f2, f1 dash, f2 dash, and if the determinant turns out to be non-zero, then it means that these are linearly independent. Determinant 0, if you get determinant 0, so what does it, how do you prove, let's say in vector space, that these two are linearly dependent?
Same columns.
So geometrically, what does a 2 by 2 determinant mean? Area of a parallelogram, right? So if the area of a parallelogram turns out to be 0, so it means one is onto the other. So these are linearly dependent vectors. Similarly, for a 3 by 3, it will be
Volume of
parallelopiped, right? If you have a 4 by 4, then you will have a hypervolume, you can say 5 by 5. Similarly, you can talk about the hypervolumes and all that, right? So again, I just say these things because everything that you do has an associated geometric meaning also. And that is something that we need to understand, that there is a geometric viewpoint also to understand the universe. So there is a very deep structure behind all this mathematics that we are doing. Okay? All right. Now okay. So let's say if you have a differential equation with these two different functions, then how will you prove that this is linearly independent?
raw मैंने लेंगे और उसका derivative लेंगे.
ले लेना मत, just take it. So you will write for those, f1 is e raised to power x, f2 is e raised to power 3x, the derivative of this is e raised to power x, the derivative of this is 3 e raised to power 3x. You take the determinant and convince yourself that it is non-zero, which establishes that these two functions are linearly independent. नजर आ रहा है ना, मतलब it can't be 0 because 3 है और एक दूसरी जगह 3 नहीं है, so it's very obvious. So anybody would like to reflect on the fact that why are we so hell-bent upon proving the linear dependence or independence of the two functions? Why are we so concerned about this? ये बहुत आइगन बेसिस के मामलात में सोचना शुरू हो गए हैं परवेज साहब, हर चीज़ को आइगन बेसिस और आइगन मामलात में सोचते हैं. Generally speaking, I mean, if you have a second order differential equation and you have two solutions and you have started off with the criteria to, show linear independence, why are you so interested to show linear independence? What will you get out of it? Why it is so important?
The solutions are taking the combinations. So you're taking the solutions which are independent of others, so they take combinations.
Absolutely. Because a second order differential equation should give you two solutions. So if you get one solution and the other solution is also the same, then it means that basically it's one solution and you need to find the second solution. So we will also engage ourselves with this task to find out the second solution. But the thing is, that is why we are very interested, because ought to have two solutions. So if one solution is just like the other, is linearly dependent, then it means that I still do not know one solution. I need to find out that solution. But you should always, keep in mind this thing, and that this involves this, and this involves this, and essentially what is the geometric meaning associated with the second order differential equation, no matter what you do. A point and a slope, or a slope here and a slope there, or a function here and a slope there. So, and that is essentially the whole task. Everywhere, to completely determine something, I need to determine constants, and I need to come up with two equations that will make me find out those two. So by the way, where does this Wronskian criteria come from? Just, anticipation, that how do you write it? So let's say you write this, C1F1 plus C2F2 is equal to 0, right? So now it's a differential equation, right? So differentiability ought to be there. It has to be continuous also. So I can write this thing as C1F1 dash plus C2F2 dash is equal to 0. And now I can write this thing as F1 F2, F1 dash F2, C1 C2 equals to 0 0, right? And if you take the determinant, in order for C1 and C2 not to be equal to 0, the determinant ought to be equal to 0, and that gives you the criteria. And that is why Zill says that this is, although you have already given the linear dependence or independence criteria, but Wronskian is a mechanical way of doing it, because you have got two equations, two unknowns, and it's differentiable. So you can take the differential and you can find this out. And because it's a second order differential equation, you will be needing function and its derivative, and no more, right? So you have to keep asking yourself, why I'm not taking second derivative? Because it is not required. Once you solve the f is equal to ma, you know that you need, when you start with d2x, you just need dx over dt and x. If you start with d3x, you will need d2x. So one less every time you. Okay. All right. So now we have one more thing. So let's say that I have a differential equation whose solution is 4 sine hyperbolic 3x minus 5 e raised to power minus 3x. And what I do know is that y1 is equal to e raised to power 3x and y2 is equal to e raised to power minus 3x are the solutions of the same differential equation. And I know that I can write this as C1 y1 plus C2 y2, which means I can write this as so if this is the general solution, then tell me, how can I obtain this solution? Because by its very definition, a general solution is one from which all the particular solutions can be obtained. So it means essentially what I am being asked is, what is this choice of C1 and C2 that will give me this particular expression? जी ये solution है, वो भी solution है. So all I am saying is, This is the solution of a second order differential equation. These are the two solutions that are known, and this is the way to write a general solution. So this is a particular solution, meaning corresponding to a particular choice of C1 and C2, I can get this solution because by its very definition, a general solution is one from which many solutions can be obtained. And this is a, by the way, two parameter family, because unlike the first order differential equation, you have two constants here and you have a two parameter family of solutions here. Go ahead. The hint is, try and open this sine hyperbolic 3x is e raised to power 3x plus e raised to power minus, e raised to power 3x minus e raised to power minus 3x over 2. So use that and try and find out. C1 is equal to 2 and C2 is equal to, अब जरा करके देखें, those of you who have not done it. If you have any problem here, then just 8 तो नहीं है, ये लिखा है C1 2 और C2 minus 7. Just write it down like this. This is basically e raised to power 3x. Right? So this will be 2 e raised to power 3x minus 2 e raised to power minus 3x and minus 5 e raised to power minus 3x. So this will be minus 7 e raised to power minus 3x. So now if you compare these two equations, you can see that for C1 is equal to 2 and C2 is equal to minus 7, you will get this solution. These things you cannot afford to forget. What does a general solution mean? What does it imply? How can you get different solutions from it? How can you construct different solutions out of it by the choice of different C's? Right? So the meaning is very important. And why do you bother about it? That's the way the macroscopic world behaves, the physical world around you. Of course, when you go to very small scales, then of course you will find a different world.
जो हमारा C1 C2 आता है वो जनरल सॉल्यूशन से पर्टिकुलर सॉल्यूशन में तब आता है जब हमारे पास बाउंड्री वैल्यूज होती हैं, राइट? लाइक वी फाइंड C1 एंड C2.
Excellent, yeah.
तो लेट्स से कि हम बाउंड्री वैल्यूज चेंज करते हैं लेकिन हमारी जो डिफरेंशियल इक्वेशन है वो फिर भी सेम रहती है. सर मुझे आई डोंट अंडरस्टैंड कि हाउ हम उसी सिस्टम को सिर्फ बाउंड्री वैल्यू चेंज करके हमारी डिफरेंशियल इक्वेशन क्यों नहीं चेंज होती, सिर्फ हमारा C1 C2 क्यों चेंज होता है? लाइक जिस तरह अगर
The C1s and C2s are found using the boundary conditions. So it means you change the boundary condition, you change the solution.
Sir, why doesn't changing the boundary always also change the differential equation itself?
Differential equation कैसे change? How can it change the differential equation? It's the solution of that differential equation. You have the idea of imposing the boundary condition is to find the unknowns. The unknowns are the constants of the solution, and the solution corresponds to the differential equation. How can you apply a boundary condition and change the differential equation? Does it make sense? Because you have already written down the solution. Now you're only trying to find out the constants appearing in that solution. That is all the boundary conditions do for you. It is a way to find out the constants so that you can write down a physically plausible solution. Because the arbitrariness is not required when you're trying to solve a physical problem.
Newton law to change नहीं.
Absolutely, yeah. That is essentially what it means, yeah. But let's say you are in the beginning of the universe and over there you change the conditions, then how the universe evolves is a very different thing altogether. Right now we are talking about something that is settled. We know this is the world around us. These are the laws it is governed by. And now I can say that this is not going to change. But if you go to the very starting point and you come up with a different condition, then of course you can construct a new universe which might be governed by a very different set of laws. Parvez is the right person to reflect on that when the time comes. I would just keep mum about it because that is all I can say. And that's also an educated guess, you know. I mean, in a different world, starting in a different way, we could have a universe which might not have been governed by the Newton's second law, it might have been governed by some other laws. We have no way to say that no, this is the only way that a universe can be constructed and has to be governed by these laws. So there is no way to say this. I think that will be too much of a claim.
H bar was bigger, Newton's law would be irrelevant.
Yeah.
It's just very small. So that's why Newton's law holds in an approximation.
Yeah. So
There won't be that.
two of the lectures that, I remember many lectures that Parvez Sahab has given, there are two of them which stayed with me and have had an immense impact on me. One was whether the constants, you know, the physical constants, are they changing with time or they are constant? So there was this one talk. Another a brilliant talk was where he talked about different disciplines in physics, and he showed that when you come down to the basics, everything behaves like a simple harmonic oscillator. So those were very, I remember you gave the talk in NCP, and it was a fascinating talk because somebody is talking about different disciplines of physics and shows you that when you get to the bottom of something, you come up with a, you know, simple harmonic motion. Anyway, and of course, simple harmonic motion, you know, it deals with the second order differential equation. So there is a relation that I'm talking about that here for a reason. Now come to the non-homogeneous second order. Okay. So in this particular case, of course, you will write down a2 of x d2y over dx squared plus a1 of x dy by dx plus a naught of x y is equal to g of x. So this will be a non-homogeneous equation. And if I write down in standard form, meaning I need to get rid of this coefficient with the leading order differential, the derivative I should say, and I can write in shorthand notation as y double dash plus p of x y dash plus q of x y is equal to f of x. I'm going to talk about some physical examples, but let me first get through the mathematical rigor, and then we will talk about what does a non-homogeneous equation mean, what is this term here essentially implying, so all of that. But at the moment, just the stuff that you need to know. How do you differentiate between homogeneous and non-homogeneous? And in this particular case, y is equal to yc plus yp, because it's a So the solution of the homogeneous part, which will be y double dash plus pxy dash plus qxy is equal to 0, will be the complementary part. And the solution that corresponds to this non-homogeneous part will be the particular solution. And because it's a linear second order differential equation, the combination of two will also be a solution. So you can show that a solution of a non-homogeneous differential equation can be written as y is equal to yc plus yp. Time and time again in books, you will find out, he will say, the solution of the associated homogeneous part is this, and the solution of that is this, which essentially means when it is put to equal to 0, that corresponds to this. When you take into account this, this is the contribution from there, and you come up with the superposition, and that will also be a solution using the superposition theorem. And that is the property that the linear systems exhibit. All right, so this much is okay. And what is the other thing that I would like to talk? So, okay. So now I go on and talk about reduction of order. I didn't do any derivation for you in the first order differential equation case because I said I'll do it for a more complex case. So let's do it now. The idea is that if you know one solution of a differential equation, how will you find the second solution? And this will be used so many times during the course of this particular, second order differential equation, because many a times you will have one solution, and I'll show you that when you deal with constant coefficients, the discriminant, when it becomes 0, you will have one solution, you will have to find the second solution, and a little story associated with that as well. Reduction of order. Okay. It's also called finding a second solution. This can also be termed as the extension of the variation of parameters to the second order differential equations. Okay? So first we deal with a very simple case and then we will deal with the special case. So he says y1 is equal to e raised to power x is the solution of, is one solution of the differential equation y double dash minus y is equal to 0. Okay? And now you need to construct or find a second solution. So already you know one solution, and you know that if I multiply the solution with itself, then it will give you a linearly dependent solution. For a second order differential equation, if you want to find a second solution, it ought to be linearly independent, and for that, as we did earlier, y2 should be u of x y1, and this ensures that whichever solution you will find will be a linearly independent solution. Okay? So now just let's plug this in, and if I plug this in, what will I get? y2, I need to go to y double dash, so I will have y2 dash is u dash y1 plus u y1 dash, and y2 double dash will be u double dash y1 plus 2 u dash y1 dash plus u y1 double dash. Now plug this in, plug these two values in here and tell me what you get. You have this and you have this. So basically I will have u double dash y1 plus 2u dash y1 dash plus u y1 double dash minus u of y1 is equal to 0. So you know, if you take u common here, so this will be y1 double dash minus y1. So one solution is y1, that means y1 double dash minus y1 is 0. So it means this becomes 0. And all that now I have is u double dash y plus 2u1, u dash y1 dash is equal to 0. Right. देख लीजिए यहाँ तक कोई when I can rub this off, just tell me so that I can continue. This is okay, right? And I just plugged it in. Now let reduction of order means I just take let u dash is equal to w. So this will become, sorry, this is okay. So this will be right. This I can write because this is dw over dx, this is dy1 by dx. So dx is gone, so what I have is dw over w is equal to minus 2 dy1 over y1, and your w now is how will you write it? So this will be, let's say, let's first write like this, log of w minus 2 log of y1, and you write down log of c. How can you write this? Right? And now this w is what? Right? And this will be and when you integrate this, so you can in fact write this thing as that is how, and then you can multiply. You know that this is u of x, y1, you know y1 already, so this thing gets multiplied with your solution and you will get it. But let's now try and do it for the problem when you have full This was way easier because this did not include the first order term, the first order derivative. Now let's do it for the case when you have this thing, y double dash plus p of x y dash plus q of x y is equal to 0. And you have to assume that your y2 is equal to u of y1. Once again, you will have y2 dash. Now your y dash will also count. So y2 dash will be u dash y1 plus u y1 dash, and your y2 double dash would be equal to u double dash y1 plus 2 u dash y1 dash plus u y1 double dash. So plug it in here. So you will have u double dash y1 plus 2 u dash y1 dash plus u y1 double dash plus p of x u dash y1 plus u y1 dash plus q of x u y1 is equal to 0. So what are the terms that will give me 0? So I can write that if I know one solution, that y1 is one solution, so it means y1 double dash plus p of x y1 dash plus q of x y1 will give me 0. Okay? So tell me which terms go to 0 here. Q of x uy1, p of x, so you take u common. If you take u common, this will be p of x y1 dash. So this will go, and what else? y1 double dash. So you will have u common, so this will be 0. Okay? So what do you have now? U double dash y1 plus 2 y1 dash plus p of x u dash is equal to 0. All right? Everybody is with me up till now? What is your name? Yeah? Yusuf. Are you following? Good. Please feel free to stop me whenever you want to, if anything doesn't make sense. All right, so now I can write this as, I will take let Thank you very much, very important, otherwise I would have been in big trouble. Thank you very much. Okay, so I take u dash is equal to w, so this becomes w dash y1 plus 2y1 dash plus p of xy1 w is equal to 0. This much is okay. This is called the reduction of order. So now I divide, first let me write everything. So this will be w dash y1 plus 2y1 dash w plus p of x y of 1 w is equal to 0. Divide throughout by wy1. When I do that, I will have w dash over w plus 2y1 dash by y1 plus p of x is equal to 0. ठीक है? wy1 के साथ throughout डिवाइड किया है, तो ये w यहाँ आ गया, y1 खत्म, this w cancels, y1 is here and y1 is gone. Okay, you are Saptan, can I make any other simplification so that I can make it integrable? So yeah, separable you can say, but just to integrate it. This is still not integration friendly. Why is that? Because this dw over dx, this is not dw over w. What I want is a dw over w, because that will make it log of w. So what I am going to do now is that I am going to multiply throughout by dx, and what I am going to multiply this whole thing by dx will give me dw over w plus 2 dy1 by dy1 plus p of x d of x is equal to 0. Now it's perfect. So this will make it omega y1 square is equal to c e raised to power minus integral px dx. So let's assume that this constant c is 1. So I will have w is equal to e raised to power minus px dx divided by square. Now this w is what? This is, so du by dx is equal to e raised to power minus integral p of x d of x. And now I will have u is equal to integral e raised to power minus integral px dx over y1 squared plus c2. I assume that c2 is equal to 0. So I will have this solution, and now I can write down the second solution. y2 is equal to y1 integral px dx over y1. So this is the form of the second solution. You don't have to memorize it. Using the method of variation of parameters and the reduction of order, you can, so this is what we call the second solution. Okay. All right. So the best thing is to apply your gained knowledge. So let's say if y1 is equal to, now I need to tell you the differential equation also. Remember, if you are given a differential equation, you cannot straight away find out the second solution. Why is that? Let's say I give you the first solution, but still, because you, yes, you have to put it in standard form. So first of all, first thing that you need to examine is whether it is written in the standard form or not. If it is not, then you have to write it in standard form, and then otherwise you will be all lost, because this px means standard form. Okay? So these are the things that you need to be mindful of. So I'm going to rub this off. So let's say you have a differential equation, x square y double dash minus 3x y dash plus 4y is equal to 0, and I say that y1 is equal to x square is one solution of this differential equation. Go ahead and find out the second solution. Yeah, hurry up. And then we will go on to talk about the next thing. So let's do it. I need to first write it in standard form. So for that I will have to write y double dash minus 3 over x plus 4 over x square y is equal to 0. So p of x is minus 3 over x. So y2 will be equal to x square e raised to power minus 3 over x dx over x4 dx. This will be x squared. This will be e raised to power 3 log of x, and that can be written as x cube. So this is x cube and this is x4, so this is dx over x. So it means the second solution is x square log of x. Brilliant. Make sense? Everybody? All right, so now we go on and talk about although we, in the most general form, we write down the coefficients as the function of x. But what if those coefficients are constants? So we begin by homogeneous second order differential equation with constant coefficients. So it means this is my equation, constant coefficients. So I assume a solution that y is equal to e raised to power mx fits the bill. Why do I do that? Because if I take 1 over x, log of x, sine hyperbolic x, sine inverse x, they are never going to give me the same function. Okay, and even in the iota form, you will have the presence of this y dash makes it unsuitable. Had there been no y dash, I could have assumed an e raised to power iota x and it would have fit the bill, because you see, cosine gives cosine in the second order, but the first order it gives sine. So there is no way that I can take something common in all these terms except when I make this assumption, because even if I take infinite derivatives, it is going to reproduce e raised to power mx with another m. So once I do that, I will have, because e raised to power mx is not equal to 0, therefore am squared plus bm plus c is equal to 0. And so what is this assumption done? If I say y is equal to e raised to power mx, and this is what I get, so in words what you will say? Yeah, so you have reduced your second order linear differential equation into an algebraic equation, which is way easier to handle. So I will have m12 equals to minus b plus minus b squared minus 4ac over 2a. Right? When you ask such questions, I'm so happy in the questions that I can answer. So M1 is minus B plus B square minus 4AC over 2A, and M2 is equal to minus B square over 4AC over 2A. And what will be the general solution? Y is equal to C1 e raised to power M1x plus C2 e raised to power M2x. The guys on the Facebook will be very annoyed with me again. Again, he has started using the board in a very strange manner. So, okay. Anyway, I should have gone there.
Who's going to be very angry? Who is going to be very
The guy is watching me on the Facebook. So one guy said,
You shouldn't care about it.
"No, I think if we are open to the world, we should learn from them also." So they have a point, because you use the board so wonderfully well. From one side to the other side, you do not make such mistakes the way I do. Sometimes I go up there, sometimes I go over there, all over the place, as they say. Anyhow, so this is what it is. And now, if your discriminant is greater than 0, then you will have two distinct roots. If you have b square minus 4ac less than 0, then of course there will be an iota. But how do you write your m? So m is basically, in that case, minus b over 2a plus iota and whatever here. So that can be written as alpha plus iota beta. And then you can actually write C1 e raised to power alpha plus iota beta x plus C2 e raised to power alpha minus iota beta x. And of course, using the De Morgan's theorem, you can also write this thing in terms of cosines and sines with the appropriate choice of C1 and C2, because sine of alpha x would be e raised to power iota alpha x minus e raised to power iota alpha x over 2 iota, and cosine of alpha x is e raised to power iota bx plus e raised to power minus iota bx over 2. So now the only thing that is problematic is when I say the discriminant here becomes 0. So you tell me what happens in that case. We have only one solution. So what will come to my rescue? Sabtain? Infinite solutions only. For God's sake, it's a second order differential equation, only two solutions will exist. So one solution is known.
The other solution is extent solution of first solution. Let's say y1 is your extent
Chalo. Okay. So, you say something. Why not x square, x cube, x4?
x is smallest.
No, my dear. This is the thing, this is the story that I want to tell you. That we were told, multiply this by this. Why? Is it revealed upon me? Why do I do that? This is all human knowledge. There is no way that you can say such things. So this is my equation. I'm going to write it in standard form. So how do I find the second solution? Okay. What is M1 in this case? Sabtan batao. When the discriminant becomes 0, what is the M1? Minus B over 2A. What is P over here? B over A. So B over A becomes minus 2, 1. So Y2 is equal to e raised to power M1x. This is minus, and this is B over A, and this is equal to minus 2m1 minus 2m1 dx over e raised to power 2m1 x. Now y2 is equal to integral. So m1 is a constant, will go out. You will have e raised to power 2m1x over, of course, e raised to power m1x over here as well. E raised to power 2m1x dx. This cancels out with this one, and you will have y2 is equal to x e raised to power m1x. And that is how you know that you have to multiply it with x. If somebody tells you that multiply it with x, how do I know that I should multiply it with x? There's a proper way, finding a second solution. Nobody ever taught us this. And this is, awful. That you ask people to, multiply something with something if something props up. Anyway, thank you very much for putting up with me. Questions, please ask.
This is before AI. Now when AI is here, I don't know what the future will.
Yeah. But now the things are so, wonderful in the sense that you can use AI to, but again the point is, what is it that you are curious about? If you are not curious, then of course, nothing is going to inspire you.